Imagine living in complete comfort. A home that's perfectly warm in winter and delightfully cool in summer, all while your energy bills shrink and your carbon footprint fades. This isn't just a dream. It's what every homeowner and business owner wants. A solution that aligns personal comfort with planetary well-being while keeping more money in their pockets. But here's the challenge we face. Traditional heating and cooling systems, which most homes still rely on, are like hungry giants, devouring energy and money with remarkable inefficiency. Gas furnaces burn through fossil fuels, while conventional air conditioners strain electrical grids during peak seasons, especially here in the Phoenix desert. As utility costs soar and climate concerns mount, homeowners find themselves caught between comfort and conscience, between their monthly bills and their environmental impact. The status quo isn't just expensive, it's unsustainable. Enter the heat pump, nature's answer to this modern dilemma. Unlike traditional systems that generate heat through energy-intensive processes, heat pumps perform an elegant dance with natural temperature gradients. They simply move heat from where it isn't wanted to where it is, like a skilled conductor directing an orchestra of comfort. In summer, they guide warm air out of your home. In winter, they extract heat from the outdoor air, yes, even in cold climates, and channel it inside. This natural approach yields remarkable results. For every unit of electricity consumed, heat pumps generate 4 to 5 units of heating or cooling energy, an efficiency rate that makes traditional systems look like gas-guzzling relics. They come in various forms. Air source pumps offer an accessible entry point, while geothermal systems tap into Earth's constant temperatures for unmatched efficiency. Water source variants provide another alternative for homes near suitable water bodies. The transformation is already underway. In the United States, heat pump installations have surpassed traditional gas furnaces in new construction, signaling a shift in how we think about home comfort. As more homeowners discover that they can save money while saving the planet, the momentum only grows. And here's where the story gets even better. The latest generation of heat pumps, powered by silicon carbide technology, pushes these efficiency boundaries even further. In a world grappling with climate change and rising energy costs, heat pumps offer more than just a solution. They provide a path forward. They remind us that sometimes the most powerful answers are the ones that work in harmony with nature, proving that comfort, conscience, and cost savings can coexist beautifully under one roof. How can microchip technology accelerate the benefits of heat pump technology to help humans achieve complete comfort? Let's go beyond the microchip and hear a story of empowering innovation to enhance the human experience. Our guest today is Nitish Satish. Nitish is a product marketing manager at Microchip Technology working out of the Silicon Carbide business unit. He returns to Beyond the Microchip today, joining us in our headquarters in Chandler, Arizona. Welcome back, Nitish.
Hey, Dana.
Thank you for joining us on Beyond the Microchip. In the intro, we briefly talked about this concept of complete comfort and why it's not so far out of reach with the growing trend of heat pump installations. What can you tell us about heat pump and HVAC solutions generally?
So in my last podcast, we talked about HVAC systems and why they're critical in AI and data center power.
Right, data center episode.
But data centers are not the only ones that require cooling, as you correctly pointed out.
Mm-hmm.
We as humans crave for comfort. And it's surprising that geographically, the Americas lead in this need for comfort and just the right temperature. Now, had it not been for a recent invasion in Europe would not have realized this either. They started flocking to heat pumps because of the non-availability of gas to burn in the winters. So imagine that in America. It may not be the same experience, but if you think about how much money is spent on fuel for your HVAC systems, you'd be surprised by the efficiency gains that you would get with the heat pumps and the pockets that you could line and, the vacations that you could take with all that money.
Yeah, so producer Claudia, who listens to every single episode, She was telling me that she lives up in upstate New York, and she had to pay $10,000, I believe, to refill her heating oil. I'm sure she'd be interested in finding a solution to that. Yeah.
Would you believe that there's a company in Helsinki that just deployed an industrial-grade heat pump to power over 30,000 homes? And by power, I mean heat the homes, cool the homes, or whatever the temperature may require. And this industrial heat pump can work at temperatures of minus 20 degrees Celsius. So imagine the scale of that.
Right. So the heat pump is just like it sounds. It's just what we talked about in the intro. Is it takes heat from one place into another. So there are temperature ranges, I think, where it loses efficiency, but for the most part, there's a gap of temperatures where it works really, really well.
That's right. So the higher the gradient, obviously, the better for the heat pump and the movement of that heat or cool air. But if the temperature gradient is not that high, then the heat pump does struggle, but it needs to be augmented with something, and modern systems are equipped to do that. So just because you have a heat pump doesn't mean that you're stuck with whatever the system's capable of or what you think it's capable of. You really have a complete system and a solution that gives you the range of temperatures that you need.
So what's the existing solution now? Does it use IGBTs or does it use traditional silicon?
So HVAC systems today use silicon MOSFETs for the low voltage residential type applications. But as you increase the ratings, or if you look at industrial buildings, for example, where you have three-phase power coming in, you would use something like an IGBT. So the difference is that MOSFETs are great for low voltage, but beyond a certain voltage, around 900 volts-ish, they start to show their weaknesses, and IGBTs really shine in those applications. Now, why there's a limitation on using IGBTs is primarily because of how inefficient the IGBTs are. So just like you have HVACs that are using traditional mechanisms, split ACs or compressor-based air conditioners, and they're moving to heat pumps, there needs to be a transition from silicon, be it MOSFET or IGBT, to silicon carbide.
So we'll get into silicon carbide in a little bit, but the idea of an HVAC system is it moves, so heating, venting, and air conditioning. That's HVAC. So the idea is moving it around. So when we talk about a gas furnace or we talk about a compressor-based air conditioning, they're actually generating the temperature, right? Is that fair to say?
It is fair to say. And if you wanted to take a step back and understand the different components from the power electronics perspective, it's really about moving this heat or cold air generated wherever to where they need to be. So if the person's located in room A, whereas this is being generated in a utility somewhere, that movement needs to happen, and that happens through a blower. So you have a fan that blows, and the fan, for all practical purposes, is a motor, and you need to drive that motor. So it's this energy conversion from your electricity to pumping the air from one place to another. Now, in the case of the the heat pumps, you would have two motors, one for the actual movement of the hot or cool air, and the other for the heat exchanger. In the other instance, where you have a traditional system, be it a gas furnace, you're just using the blower to move the hot air generated by the furnace in this instance. Or if you need to cool the temperatures, you have a compressor-based heat exchanger even there, and then you move that cool air over to the other room.
Right. So traditional solutions, you have a refrigerant, and the refrigerant then generates the cold that the fan blows.
Correct. Yeah.
Throughout a central air system.
And this refrigerant needs to go through a compressor because the nature of the refrigerant is that it gets cool when it's compressed.
Right. And then it needs to be refilled.
Exactly.
Okay. And then on the other side, you've got a combustible source for heating. So whether that's heating oil or whether it's natural gas, you've got a system where it actually has to burn a fuel, and then that heat needs to be captured and redistributed.
Right. So I was reading about a country in Eastern Europe which has city-wide heating, and it's great when the temperature is really cold because it dates back to a few decades old, right? So, it doesn't work today where the temperature fluctuations are intense. So you could have an autumn where the mornings and the evenings are really cold, and then the day it gets warm. So if it gets really cold, it's great. But then the system that the city developed is that they need to have this consistently over a few days, and only then will the heating turn on. Now, the concern there was, again, how expensive it was to heat the whole city. if they were to move to what Helsinki did, for example, they, could reconsider their whole thought process on how expensive it might get and, how efficient the heat pumps could be.
At our campus here in Chandler, Arizona, where we are right now, there are 6 main buildings. For those of you that want to check it out on Google Earth, you'll see that there's 6 main buildings. One of those main buildings, to my understanding, is just the air handler. And if you go outside, one of the reasons that we're far away from it right now is because it's so loud and we don't want the microphones to pick it up. But the idea that a campus that houses a couple hundred employees has to have a dedicated building just to HVAC. And my understanding is it's not a heat pump. I think it's more like a swamp cooler or something.
That's exactly right. So the scale of these are immense. And as you can imagine, as the scale increases, so does the complexity of the systems. So for a building this size, you would still need to have the blowers, whether it's a traditional cooling system or whether it's a heat pump. What would change is the fuel for this cooling or heating. Mm-hmm. And that's where the energy gains would come from. So to give you an example, the heat pumps are 5 to 6 times more efficient than a traditional HVAC system. That's the improvement in just the heating or cooling efficiency. Now, the efficiencies that you could gain by using different power electronics topologies or power electronics devices could be in addition to whatever gains you're getting from just the technology.
So are we talking about reduction in energy consumption, or are we just talking about efficiency?
We're talking about efficiency in a manner of speaking where you move the hot or cold air from one location to another. Now, that could mean less energy consumed to generate that hot or cold.
Okay, so that's really what we're talking about is the traditional methods right now burn so much energy unnecessarily.
Exactly.
Okay, so that's our power bills are high because we're wasting. Is that a fair assumption?
It is.
Okay.
The other assumption is every time you start a motor, you have a spike in the energy consumption. So the compressors, for example, people ask you not to turn off your refrigerator for 2 reasons, right? One, you have food in there, it gets spoiled. But the other really is you have to maintain it at a temperature where you're optimizing how many times the compressor turns on. If you're not doing that, if you keep it too cold or too warm, for example, you have the spikes in energy bills.
All right, so you want to maintain that consistent temperature. Okay, that makes sense. So if you look at your thermostat on the wall, you've got a temperature that you set, and ideally what happens is when the temperature goes up, that's when the compressor kicks on. So whenever those two because in Phoenix, if you have a 2-story house, even some 1-story houses, you probably have 2 compressors. And so in order to keep those temperature areas at a moderate level, those things are going to fire up. And every time they fire up, it's a 240-volt system. And so I imagine in some areas, you'll actually see the lights flicker when that compressor fires up, if it's sucking that much energy?
As possible, yes.
So we're looking at increases in efficiency such that we don't have to deal with that?
So the light flickering is because of 2 reasons. So one is the energy being consumed, so there's a redirection of energy towards the heat or the compressor.
Right.
But the other reason is also the EMI that's generated. So people talk about radiation from your phones and from so many other things, but they don't talk about often the EMI generated by machines, heavy machinery.
Right.
So those are the 2 reasons why the lights flicker. But yes, there is a redirection of energy, and that's why you have that.
So that would bring us to our efficiency question, and this is where silicon carbide comes in. So where does silicon carbide come into the heat pump itself?
So silicon carbide will be used in the motor drive. So the motor drive could be powering the compressor, where it's, reflowing the refrigerant, or it could be pumping the air in the fan.
Okay.
So in both of these areas, it's critical to use something that's efficient. Now, silicon carbide may or may not be the right solution depending on if it's a residential use, if it's just a few kilowatts that's needed versus a few megawatts that's needed. So depending on the scale, you have the right technologies to choose.
So across the various range that you're talking about now, we're talking about size of dwelling, we're talking about energy needs. What kind of products are we talking about? What devices would we put when we talk about silicon carbide?
So silicon carbide from Microchip is available in various forms and footprints. So you can have a die that you can package into a device of some sort. It could be a discrete or it could be a module. So the low end of the power range would use discretes typically. That would mean a TO247, a TO220, a SAT227, TO263, whatever the package name may be.
What kind of power are we moving around with those?
So typically the crossover point from discretes to modules is about 30 to 50 kilowatts. So within 30 kilowatts, you definitely would use discretes. But between 30 to 50 is a gray area. It's a design choice. Beyond 50 kilowatts, it's easier to use modules. Now, I mean, there may be instances where discretes are used, but you just have so many of them in parallel. Going back to the EMI topic,
right,
that complicates that.
So suppose one of our listeners has a use case for this technology. Where could they go? Where would we send them?
So Microchip prides itself in how we bring silicon carbide to the market. We want to allow our customers to adopt silicon carbide with ease, speed, and confidence. So go to microchip.com/SIC.
So I would imagine that you can check climate science modules. It always happens during hurricane season, but you can look at average temperatures and they're probably on the up and up. Now, we're not going to get into why that is. I just want to state that that's the way it is. So we can expect these fluctuations, and they're going to hit our wallet. So do we have any future predictions on HVAC solutions like heat pumps? What's coming? What should we be aware of?
So you may be familiar with the name Carrier, which is a century-old name in the households in the U.S. especially. Mm-hmm. So they had a recent pivot to building more heat pump systems. So they were doing it locally here, but they also acquired a company out of Germany to reinforce their message that, hey, heat pumps are the future. So when you have a conglomerate or a huge company like them focusing the shift towards heat pumps, you know that's going to be the future.
They're disrupting themselves.
They are disrupting themselves. So they're cannibalizing on all of the HVAC business that they had.
So definitely keep an eye on something like that. And then we kind of talked about this offline, but heat pumps are not inexpensive.
So when you look at a heat pump, you look at the sticker shock and say, oh, it's so expensive. But you always have to look at the cost of ownership, right? And that also goes back to how silicon carbide can play into heat pumps because, yes, silicon carbide is more expensive, but if it makes your system more efficient, if it makes your system more reliable, then that might be the right solution for you. So instead of lasting 5 years, can it last 10 years or 15 years because you're using silicon carbide? Then doesn't that account for the payback time? I think yes.
When you're thinking about a household expenditure, you want to get your money's worth and you want it to last as long as possible.
Right. And going back to your point on we're starting to see these fluctuations and these increases in temperature, that ROI can just get shorter and shorter with these cycles.
Yeah. So think about the monthly waste that you get in your power bill and then think about the longevity of the equipment lifetime. So yeah, I mean, it's a lot of math to consider, but efficiency is always good.
Yep.
Any final thoughts, Tish?
So Microchip has a wide variety of products to offer for heat pumps. We have products ranging from 700 volts, which would be great for your residential heat pump applications, to all the way to 3.3 kilovolt, which you may need when you're talking about industrial grade heat pumps that are powering cities. So come look at microchip.com/SIC and we'll have the right solution for you.
Thanks, Nitesh. Nitesh Satish is a product marketing manager at Microchip Technology. He specializes in silicon carbide and power modules. He joins us today from Chandler, Arizona. Thank you for venturing beyond the microchip with us. Join us next time as we continue to explore empowering innovation to enhance the human experience.